In today's lecture, we're going to be looking at Kepler's first law and how to determine the eccentricity of an orbit. One of the primary changes that Kepler made to the Ptolemaic and Copernicus models was he took the planets from being in circular orbits and actually proposed that they were in elliptical orbits. So Kepler's first law basically says that the planets have elliptical orbits. They orbit the sun in an ellipse instead of perfect circles. Now, one of the primary concepts that you're going to look at is you're going to see that every planet doesn't have the same eccentricity, or how much unlike a circle is its orbit. So what we're going to look at now is how do you determine the eccentricity of an orbit? Well, one of the primary things we're going to do here is you have this demo in your actual class where you can change the you have the eccentricity demonstrator provided by the University of Nebraska labs. Okay. So there's two primary ways that you can actually calculate the eccentricity of an orbit. The way that we're not going to be demonstrating here is you could take the distance between two foci, so the two x's, you can measure that distance, and you could divide that value by the length of the major axis. The major axis would be the farthest points in its orbit out here. Once you divide those, you're going to come up with a 3-number value that is going to be, of course, less than 1. Okay, well, that right there is how eccentric is the orbit. So what is the eccentricity? You're going to get a number as you see over here, this value over here. So now we're going to demonstrate the other way that you can actually do this. One thing that you can look at is one foci is, of course, always going to be the sun. And what you can do is you can take the value of C. This is the very center of the orbit, and this is the location of the sun. And so what you can do is you're going to take that value, which is C. In this case, it is actually 60. And you are going to divide it by the length of the semi-major axis, which is, of course, the value of A, as you can see here. So the question is what happens to the eccentricity of an orbit as you change these values? Well, we're not going to focus on C. We're going to go ahead and leave that at like 50. A nice even little number there. We'll go ahead and just type it in. Okay, and now what we're going to do is we're going to actually change the orbit of A, and we're going to see what happens to the eccentricity of a planet. So let's say that we start going like this, and we start changing the value of the major axis. Okay, well, with this, what you can do is you can see it's starting to go down in its value. So its eccentricity is becoming less eccentric. So 0.515 is less eccentric than 0.61 or 641. Okay? So now here's some of the questions that we're going to address. We're going to go ahead and leave this at, let's go ahead and leave it at 80 right there. Okay. So now the question is what happens whenever you change the distance to of the sun from this? All right, so look at the values here. As those values get farther and farther apart, look what's happening, okay? So as you decrease the value of C, let's go ahead and make C absolutely 0. What do you notice about the orbit? The orbit of the planet is going to be perfectly circular. So now what we've actually figured out here is that if you only have one foci, so if the sun were at the exact center of the orbit of one solo planet, what you're going to see is that planet is going to have an eccentricity of 0. But let's take it on up and see what happens as we start to get the sun in the imaginary position. We keep on going, we keep on going. And then you can see that the highest value we can go to is 79. Well, here's the thing about this. What do you notice about this value? It's coming closest to the value of 1. Well, if you could actually achieve the value of 1, the shape of this actual orbit would be a straight line. And that's one of the key concepts. So what you can see is by looking at the value of the eccentricity, you can determine how unlike a circle it is, or how like a circle it is. And it's all dependent upon what's the distance between the foci and the center of the orbit, or you can look at what is the actual shape or how far away the actual orbit is the semi-major axis. Okay? This concludes the lecture here on Kepler's first law. Again, it's the law of ellipses, and it talks about putting them into different orbits based on how unlike or like a circle they are.